And with us, we can move to our second paper, which is going to be presented by a group of researchers. They are all computer science PhD students at KIT, the Karlsruhe Institute of Technology, and they are part of the research and training group Energy Status Data, Informatics Methods for its Collections, Analysis and Exploitation, and they look at the handling, processing and analysis of complex energy data. And as far as I understood, Florian Kalinke is going to start off, and then your colleagues are going to take over the microphone. The paper is entitled An Evaluation of NILM Approaches on Industrial Energy Consumption Data, and I look very much forward to your talk. Florian, the stage is yours. Please go ahead.
Okay, thanks a lot. So can you see my screen and hear me?
Perfectly fine, both of it.
Perfect. Okay, so welcome to our presentation and thanks for the very nice introduction. Our paper is titled An Evaluation of NLM Approaches on Industrial Energy Consumption Data. And we split the talk in roughly 3 parts and we change in between, just so that you know what's coming. So our talk is a bit less technical than the one before, because we basically published a new data set, but we have some insight which we think and would like to share with you. So why are we interested in doing load disaggregation or non-intrusive load monitoring? Because we know, or we think, that a better energy management can reduce the global energy consumption. And by using load disaggregation, we can identify the appliances which use the most energy. And also we know that, for example, in Germany, the industrial sector is responsible for 46% of the total energy consumption. So it makes sense to reduce the consumption in this sector. And there you see a picture of how energy disaggregation works, but Snigdha will go into some more detail on that later. So just to restate the problem in a concise way, there are potential energy savings in the industrial sector, which are probably very large, but we noted that on the most load disaggregation algorithms or methods have only been tested on household data sets. And we think that this is because there is a lack of available industrial energy consumption data. And so we try to close this gap. First of all, what are the differences between industrial and household energy data? And actually, another group of PhD students from the same research training group 3 years ago published a paper where they pointed out 4 major differences. This is the device inconsistency, instance dissimilarity, interday inconsistency, and device dependency. And based on their on these differences, they conjectured that the algorithms designed for household energy data, they do not work in an industrial setting, and they did not validate this claim. So here's our paper. We try to identify and describe specific differences between industrial energy data sets. We show that the disaggregation algorithms which work well on household data do not necessarily do so in industrial data. And also we publish a data converter which is compatible with NILM, and I guess most of you know this, but it's in our opinion, the de facto standard for load disaggregation. And yeah, it's based on the data set which was published before. So with that said, I pass on to Snigdha.
As Florian has already introduced the term load disaggregation, now to make the term load disaggregation a bit more clear, we have this mathematical formulation with us, which shows that the total power of the machines used in any industrial or in household setting is kind of disaggregated at the individual machines. And we are really interested in this, the power consumed at the individual machines of this, and this is what is load disaggregation. So it is like finding out the individual load consumption at the machines with respect to the total power consumption. Next slide, please. Yeah. So now taking a step back, what other people has done in these areas, there are several classical algorithms and neural network algorithms exist to find out the load disaggregation. For example, the combinational optimization factorial hidden Markov model, and in neural networks there are sequence to sequence, RNN, and so on and so forth. As we know, it is important in case of a machine learning algorithm to have the evaluation matrices. There also exist several evaluation matrices. So, for example, normalized signal aggregation error, shortly abbreviated as SAE, or normalized disaggregation is NDE. And we, in our paper, also used these two matrices for evaluation of the of our algorithm. Then in above algorithms, all of them are implemented in the NILM toolkit. So in our case, we have chosen ML which we use as a baseline and evaluated the matrices based on SAE and NDE. Then we come to the data set. In our paper, we kind of used 3 data sets, which 2 industrial data set and 1 household data set. We introduced HYPE data set in our paper, REDD as a benchmark data set, which is commonly available as a household data set, and IMDELD is a data set which is a food process, which is collected from a food processing factory, which is basically an industrial data set. In our work, we kind of divided the data set in several points. For example, several attributes, types, appliance activity, and parallel uses and all. We have figured out in case of industrial data set, that is appliance activity is kind of working hourly. However, in case of the household data set, it can be anytime. If you look at the parallel usage feature, it is in industrial data set, it is kind of frequent. However, it is not available in the household data set. Now we come back to the types of appliance. Depending upon the type of appliance and the behavioral pattern, they can be categorized as 3 types. One is type 1, 2, and 3. So basically on and off state, multiple states, and continuous states. So also it's another important point is the total demand. If you see it here, the total demand can be small and large in case of industrial data set. So it is not only small or only large, it can be both small and large in case of also in industrial data set. Next slide. Here, whatever we discussed and talked in the previous slide, we can see here in the dataset diagram. Here, the first is HYPE data, the second one is IMDELE data, and the third one is REDD data. As you have already discussed, we can see the order of magnitude is kind of is small in HYPE data and large in IMLEDD data. And also you can clearly see the cyclic pattern present in IMLEDD and RE data. However, it is not available in the HYPE data. And I think that is because of the machines used in HYPE data is kind of different from the other machines used in the industrial data set. Okay, now I'll pass on to my colleague, Pawel.
Thank you, Snigdha, and hello everyone from my side. So my part here is to explain the results of our analysis to you. I will start with describing the table we see here on the slide. In the first column, there are the 3 data sets that Snigdha already described to you. Then the second column is the type of devices. So we can see, for example, that the HYPE data set can be divided into 4 groups with only type 1 devices, only type 2 devices, only type 3, and all the types of devices combined. And then we see all the remaining columns to the right are the algorithms, including the mean baseline. The table is divided into 2 parts, and the top part is the SAE evaluation results, and the bottom part is the NDE evaluation results. Next slide, please. So the first observation is that if we ignore the types of devices, so if we just take a look at the data sets as they are, it seems to be that one of the algorithms, the neural networks sequence to sequence, performs best according to the SAE metric. However, if we take a look at the different metric, at the NDE, we can see that it is not the case in the terms of the RADD algorithm. So the summary is that there seems to be a trend. However, the best algorithms sometimes also can depend on the type of metric we choose. Next slide, please. If we take a look at the more fine-grained level, so now we are also interested in specific types of devices, then the one very surprising result was that for type 1 appliances for the HYPE industrial dataset, it was the baseline, so the mean prediction that had the best results. And this is very surprising because we have seen before that if we look at all industrial datasets combined, then there seems to be one algorithm that works best, but for a specific type of device, it is actually not the case. Also, we can see that for type 3 device of HYPE industrial dataset, it's also a different algorithm than the sequence to sequence, namely the DAE that performed better. So the summary of this slide is that if the algorithm performs best in overall, it doesn't mean that it will perform best for also specific types of devices that are in the dataset. Next slide, please. Another general observation is that the modern neural network-based algorithms perform on average better than the classical algorithms. So we see here a tendency towards neural networks. However, still the surprising result from the mean baseline prediction that worked best in one case. So, so a summary of this slide is that even though there is some trend, the neural networks perform very well. Still, for some situations, simpler algorithms might be might be better than the more complex ones. Next slide, please. The last observation here is the difference between the type 2 and type 3 devices. So type 2 device is, just to recap, is a device that can have multiple states of operation. Whereas type 3 device is a device that has so many levels of operations that we actually call it continuous device. And so in the literature, especially the literature that introduced this classification into 3 types, there was an assumption, a hypothesis that type 3 devices would be much more hard to disaggregate. And our results have shown that this is not the case, not for all algorithms especially. So we can see that there are algorithms that have better performance on a type 3 device, which actually should be the harder one to disaggregate than on type 2 device. So this is a new observation. We did not expect this to happen. And now I would like to pass back to Florian.
Okay, sorry, my mic was off. So to sum up our presentation, what we observed is that benchmark data should include appliances of all types. And as Pawel already pointed out, a dataset with, say, only type 3 appliances, which is, according to literature, difficult to disaggregate, can draw a wrong picture of the performance of an algorithm. And from this, it also follows that we need diverse benchmarks for low disaggregation algorithms. And as our main table shows, the industrial data differs from household data and also from other industrial data. So it makes sense to include both types of data for measuring the performance of algorithms. In our opinion, possible next steps are to investigate the reasons for the large discrepancies between data sets. And also what we think could be very valuable for industrial data is to incorporate domain knowledge into low disaggregation. because in many factories there is a lot of processes which repeat themselves or which are known, and algorithms for low disaggregation should be able to incorporate this knowledge. So we're now available for questions, and thank you for listening.
Thank you very much to all three of you for this nice presentation. And the floor is open for questions here in Zoom, in Slack, chat, or verbal. Please go ahead. Maybe I may start with a more general question. Where do you see the applications for disaggregation and non-intrusive load monitoring in the industrial context? I mean, in the private context, it's rather clear, energy saving tips or privacy invasion. And on the other hand, in the industry setting, I could always install a meter on every machine. So where do you see the big point here?
So we see the big point for regulatory let's call it stuff, because sometimes you have to do an energy audit, and it would maybe be possible to automate something like this. And the argument that you can install your energy meter for each machine, I mean, this does also hold in the household setting, but it's just so much easier to automate it with a single meter only.
Absolutely. Thank you for this good answer. Another chance for the audience to pose questions. So I also noted that using side knowledge may be an interesting feature. You mentioned it here as future work. Can you maybe comment what kind of side knowledge this would be? You've already started like production plans or something, production cycles. So you probably could what's your estimate? How well could you improve these algorithms then?
Okay, I think it's hard to provide a general answer there, because I mean, it depends on the factory. But for example, for our data set, there is a lot of background knowledge. There's 2 vacuum pumps, for example, and if one of them does not suffice, then and only then the other one starts to work. And I mean, we know this, but the algorithm doesn't. And things like this could potentially be incorporated in the algorithms.
Mm-hmm.
I can add to this answer. In case of our HYPE data, there are a lot of device dependencies exists, and which can only be answered by the domain experts working in there. So by maybe talking to them, or by maybe extracting the knowledge from the domain experts, which we can collect this device dependencies, and the device is dependent on the other or not, and which is, as Florian mentioned, is difficult to extract from the data analysis and understanding from the data. So maybe we would like to integrate that and improve the result. That's the future plan.
Thank you.
Okay, so just
Sounds
to
like
add
a very good endeavor. Mm-hmm.
Okay, thanks.
Go ahead, please. No, please go ahead.
One small thing. We uploaded our code to GitHub. So if anyone's interested in using the data set, he's free to do so. And I think this morning I also sent a pull request to NLMTK, so it might be included in future versions. So yeah, potentially very easy to use, and I hope everyone can use it for their analysis purposes.
Excellent. Thank you very much. I think especially in the area of energy disaggregation and NILM, we are very interested in reproducible research, which of course is fueled by code sharing. And I think this is exactly the way to go. So thank you very much again to all three of you. And we can now continue to our next 2 presentations. These presentations will be given as video presentations, and they will be live in the NA Mirror, the North American Mirror, later today. I've seen that in other sessions, sometimes we had authors present. So if this is the case, then we can discuss the 2 video presentations right here, at least a little bit. And otherwise, I would ask you to phrase your questions to the next presentations in the Slack channels, and the authors will then asynchronously answer these questions. So if I may now ask our Zoom masters to
Yes.